In this video, I want to look at the general case of projectile motion. And so it's a special case of just general two-dimensional motion. As long as the trajectories don't go that far, you're near the surface of the Earth, we can assume sort of the flat Earth approximation. And so we want to look at it in general, but it has a number of assumptions that you really have to keep track of. It's really kind of a danger because what we're about to derive only applies in a very limited subset of circumstances. But since the circumstances show up now and then, it's useful to not have to rederive them every time. So let's look at those assumptions now. So what we're assuming is that we're in fact assuming a coordinate system where x is horizontal to the Earth, y is perpendicular, and we're assuming that we have a projectile that starts at the origin and is launched with some initial speed v0 at an angle alpha naught from the horizontal. So these are all assumptions that you have to remember if you're going to use these expressions. And so let's see what that gives us then. So our initial point in time is then the launch time, and then we're looking for an arbitrary later point in time, t. So what do we have? So we have two dimensions that we'll have to look at. So in our first dimension, we have, let's go down here. Our initial x position is equal to 0, and our final position is unknown. We'll call that x. Our initial x component of the velocity is our initial speed, v0, cosine alpha naught. And our initial x sub I, we don't need the 0 in there. Our initial x component and our final x component of the velocity is equal to v0 cosine alpha naught, and that is because there is no acceleration in the x dimension. And so we're going to say that our initial time is equal to 0, and our final time is then equal to some generic time t. This tells us that delta t is just t. So now, if we look in the y dimension, our initial y is 0. Our final y is unknown, so that's just y. So our initial y velocity is equal to v0 sine alpha naught, and our final y velocity is unknown, so I'll just call that v sub y. Our acceleration in the y is towards the center of the Earth, so that's a negative g, and our initial time is 0, and our final time we'll call t. And so what else can we say about this system is that initially we can link our velocity, our speed is just the sums of initial x plus initial y. That's just sort of given by the trig, how we've defined it. But we can also relate then our angle, tangent of alpha naught, is equal to the initial y over initial x, tangent. Right. So that is a way to relate some of our parameters initially. We also know that at the final time, then, I think probably, that's a whole lot of yellow. Move on to something else, I suppose. So our final, then, we have our final speed is the square root of vx squared plus vy squared, where vx squared is the same as the initial. And then, if our final velocity makes some angle alpha with the, at some time later, has some different velocity that makes some different angle alpha with the horizontal, that is equal to the final y component over the final x component of the velocity. Okay, so those are sort of the expressions that we know. So now let's use this in general for our kinematic equations and see what we come up with. So in the x dimension, we have it's uniform motion. There's no acceleration. So x at some later time, at the final x, which is just x, is equal to the velocity in the x direction times the time interval, which in this case is just t. Now in the y dimension, our final y, which is we just call y, is equal to the initial y, which is 0, plus the y component of the initial velocity, which is v naught sine of alpha naught times time, minus 1/2 g t squared. This is the acceleration, which is negative g, and delta t squared, which is just time squared. And we also know that the final y, vy, is equal to the initial v naught sine alpha naught plus the acceleration times the time interval, which is minus gt. So we can, if we solve this for time, time is x over v naught cosine alpha naught, and then I'll substitute this into here for time. And what does that give us? So this gives us y is equal to this first expression, v naught sine alpha naught times the time, which is x over v naught cosine alpha naught, minus 1/2 g, and then this thing squared, x over v naught cosine alpha naught squared. And so if we go ahead, simplify this, v naughts cancel, this turns into tangent. We have an expression that relates our y component of the position to our x component of the position. Y is equal to tangent theta naught x minus g 2 v naught squared cosine squared alpha naught x squared. And so this is the parabolic motion. Parabolic motion of projectile motion. The y is a function of x. These are constants, and so you have a linear term in x minus a quadratic term in x. And so if you have a parabolic motion, or you have projectile motion, this might simplify some of the calculation. The key being you always have to remember your assumptions. Okay, so let's do a simple example of, we'll just do a simple example of parabolic motion here. And so let's say we have a person and they're going to launch a ball 30 degrees from the horizontal, 24 meters per second, and they're going to launch it 1/2 meter above the ground, and it hits a wall some 40 meters away, and we want to know how high above the floor. High above the floor. Well, we know the initial speed launched. We know the angle launched. That's alpha naught and v naught. We know g, and we know x. This is our x, so that's 40 meters. So we could use our equation for parabolic motion to see what's the final y position. So let's just plug that in here. And so y is equal to tangent of 30 degrees is 1 over the square root of 3 times x is 40, so that's 40 over the square root of 3 minus, this is 9.8 over 2, 24 squared. So cosine squared theta naught is 3/4, or the square root of, or inverse then is 4/3 times x squared, which is 40 squared. I can plug that into my calculator, and I get, this is sort of 23.1 minus 18.1, and this will give me 5.0 meters. Is that our answer? No, it is not our answer. Remember, our equation for parabolic motion assumes that the launch point is at the origin of the coordinate system from which all of these things are referenced. So to use our equation for parabolic motion assumes that the zero of the coordinate system is at the launch point, which was a half a meter above the floor. So the ball hit here, where that's 5 meters, and if we want to know how high above the floor, so that would be 5.5 meters above the floor. Okay, so parabolic motion, if you don't need time, you simply want to link the x coordinate with the y coordinate. This is a very handy expression, but you have two problems. You can't use it where it doesn't apply. You always have to remember the assumptions that go into using that expression, and if you just plug numbers into the equation without thinking about those issues beforehand, most likely you'll get the wrong answer.